Alright, today I'm going to do a video about the topology optimization in Fusion 360 and how I made these super sweet brackets to hold up my Raspberry Pi touchscreen onto this shelf. You can see the brackets, quite organic shaped. I think they look pretty sweet, but let's hop into Fusion 360 and see how they're made. Okay, here we are in Fusion 360. I'm not gonna walk through the way I designed it, but you can kind of see it in the background here. There's lots of good tutorials for design of Fusion 360 if you want to search YouTube for those, but really trying to focus on the topology optimization. So we'll try to jump into that now. We have our part designed, and we can see just the geometry of the bracket. And now we can start our optimization process. So first thing we're going to do is go into the simulation tab of Fusion 360. And we can see there's lots of different options, but what we're interested in doing is this shape optimization tab. So we're going to go ahead and select that and create a new study. We can see our part is now in the simulation workspace of Fusion 360. And we have a new study already begun. So with our part, what we want to do is have this side mount to a wall and this side holding the Raspberry Pi that we saw earlier. And so we're going to set up constraints and loads that represent the actual case that we're going to put under in real life. So we'll start with setting up constraints. And what we're going to do is we're going to fix the two holes that will be screwed to the wall, and we'll fix it in X, Y, and Z directions. And that's why you can see that little lock on there, and it says fixed. Alright, so that's really the only constraints we want to put on. We can then apply some loads to our part. So the first load we want is on this screw hole, which is going to be basically the weight of the Raspberry Pi in the screen, as well as any moment that comes from it hanging off kind of an edge. And we're going to apply the force using this vector tool. We can see up here in the Y direction is really the direction of our weight. So we're going to put in maybe negative 20 newtons. That's much larger than anything we'll actually see. And then if there's any moment that's caused by it hanging off the edge, maybe we'll add something spinning about the Z in the X direction, and that'll make a little bit more sense once we add the other one, and we'll put in the opposite direction for the X force. But it's pretty plain. You can see in the window the blue arrow shows up to show you where the force is being applied, because this hole is blue, and then the direction of the force being applied through that arrow. Cool. So we'll do that. And then we'll apply another load. We'll apply it to this hole. Again, we'll go to the vectors. Same weight. But this time we'll do negative 5 to kind of create that moment of a weight hanging off the edge. And click OK. Cool. So at this point, if we wanted to, we could run our simulation, but some funky things could happen because we haven't told the program we want to save any material around the bolt holes. So it's possible that it could just remove all the material, say like above or below some of these bolt holes, if we don't tell it specifically to save those regions. So we'll go into preserve regions, and then we'll start with these holes. Select these holes. So right now it's just preserving that circle, which it probably would have done anyways, but we want to preserve a region larger than that. So we'll go ahead and type 8 millimeters in here, and that looks like a better region to preserve. And we'll do that for the other one. And finally we will select the entire face, not the edge. And this one's a little bit smaller, so we'll do 7. And again, 7. Cool. So now when the optimization runs, we'll still have plenty of room to add a bolt and have area for the bolt to push up against. So see, we can solve it now, but before we actually solve it, we'll go into the settings and go into our mesh. And here we can decrease the mesh, which will make it a much finer resolution when we solve it, which will create a better part, but it'll take a little bit longer to run, which I'm okay with. Cool. So now I think we're all ready to solve our part. So we'll go up to solve, hit solve, and then we'll see this solve page come up. And if you have multiple studies that are ready to solve, they'll show up here. But since we just have one, we can select our one study and hit solve. And then Fusion 360 is going to send this to the cloud. You're only allowed to solve topology optimization things on the cloud. And so it's sending it right now, and then it'll begin to solve it in a second here. And we'll go ahead and fast forward through all of this. Alright, so now we have our simulation completed, and we can see the results that came out. Pretty sweet looking part. This bar on the right, we can adjust how much material the part is comprised of. Right here we can see the mass ratio, so this is comparing the original mass of the part to this new design of the part. So we can see 28%, roughly a 75% decrease in mass is really quite good. You can rotate it around and see kind of cool geometry that showed up. Some funky holes showing up, some like holes in here that go out through the sides. Looks pretty sweet, if you ask me. So I'm going to just leave this on whatever target. I'm not really sure exactly what that means, but we'll leave it for now. Now we want to bring this into our design space. So go to Result Tools, and we're going to promote this. We want to promote it to our design workspace if we're going to try to 3D print this. You can also do other things with it, but we just really want to make this actual part. So we're going to put it into our design space. So now we can see both our original part and our optimized part kind of sitting inside of there. So we're going to go ahead and hide the original shape and just look at our new optimized shape. So we can kind of see from the simulation there's kind of some jagged edges. Nothing too bad, but I really want it to look nice and smooth, nice and organic. So we're gonna change that. And I've already done this, but right here you're gonna want to turn. You're gonna want to click this Do Not Capture Design History. And so you can see right now there's no option up here for mesh. But right now we're working with a mesh body. So if we turn off our design history, continue. Now we have this option to play with mesh bodies. And then under Modify, there's a nice easy tool for smoothing our part. And we just want to select this part. And so we can see even with a pretty small amount of smoothing going on, it's gotten rid of all of our jagged edges. So I like that. I'm going to go ahead and leave it as that. Cool. So this is the part. We're going to go ahead and print it out. But before that, I'll make some quick comments. Like these holes, you can see even though we did preserve region, they don't come out as perfect holes. They kind of have these rounded edges. And that's not because of the optimization, that's because of the smoothing that we applied afterwards. I'm okay with this, but if you want to, you could add geometry that made those holes exactly the way you wanted. But again, I'm not actually worried about the strength of this. just as long as it looks cool. Yeah, so to be able to actually print this, we'll go ahead and save the mesh body that we're working with, our smooth optimized part, and we'll save it as an STL. And I'm just going to leave it as that name. That's fine with me. Cool. So now can look at our STL in here. Sure. Do whatever default Microsoft has. Just to look at it real quick, and we can see it's nice and smooth, and I think it looks pretty cool. And then one more note that about the printing, we're going to print it in this orientation, so it's going to be printed kind of flat, and this is because the layers, the direction, the orientation of the layers is important to the strength of the part. So a 3D printed part is weakest in the perpendicular direction to the layers. So in this case, it's weakest if you pull this part and this part, because that's where our layer is going to be. But that's not the direction we care about. We care about the load being transferred across here. And so we're going to print our layers so that they kind of fill this whole volume. Yeah, so go ahead and do a quick time lapse of the print, and then show you the final brackets and everything mounted up. So I didn't do a great job explaining it, but basically printed parts are strongest in the plane parallel to the print bed. So hopefully that makes sense why we're printing it in this orientation. This part was printed on a Prusa Mark III, which is a super nice printer. If you have the money to afford it, it's still pretty cheap, but I have a much cheaper printer than this. And then I'll apologize. It was nighttime when you were printing it, so you can see how dark it's getting. But here's the final part. The print came out really nice. We printed 2 of them, one for each side of the screen. So yeah, we'll go ahead and take a look at the final products. Alright, so here's the final bracket, holding up my Raspberry Pi screen. Yeah, I'm pretty excited about the way it came out. If you have any questions, go ahead and drop a comment. If you like the video, go ahead and drop it a like, and subscribe if you're interested in more content like this. Thanks for watching.